The data problem is quite widely known, and to be honest, the kind of problems that occur in electronic warfare and CEMA databases occur in most databases. And part of that is to do with the sheltering of information, and part of that is to do with lack of definition. So these are some of the recognizable problems that people may already be aware of. When we consider those kinds of problems, we see solutions to those which appear in electronic warfare and CEMA, and we also see approaches to that which help to develop data and also approach the data problems in data science and AI approaches. And obviously there is some kind of mix of those two that could be beneficial. There are many databases available, many electronic warfare. They do kind of have different shapes and different structures, and some of them have different processes and facilities. But a generic form of a database could be something that looks like this for electronic warfare, and it has a structure which has relationships between records, and we can sort of recognize this as a relational database, or even an object-oriented database, but more commonly they're relational databases. And we can see that there's sort of a part here that's about decision making, about modeling, and it's about tactics. It's sort of proof obligation and decision assistance. There's a part here that might be about building up networks, personas and logins, and working out who talks to who and when, and who's a relay and who's a commander type thing. Then there's an area that's about the operational order of battle. It's the geographical layer, and it's used for situation awareness and may be used to prepare operational tasks based on geography. There's also a countermeasure tactics part, which is a specialized part of the database. And then there may be parts that are to do with test and validation and production assistance. And then the larger part of it is about weapon systems analysis, or threat analysis, or even ELINT and SIGINT activities. And that's actually what's the most common element within all of the databases shown. So that kind of database, we can sort of see that there's actually sort of a few users of that, and it's fairly complicated. It is a generic one, it's not any specific database here, but it just shows you that there are multiple users that come together in order to use this database and cooperate. So it becomes an area of where people share information. And one of the things we have to do out of that is, in the process of this, is create threat vulnerability assessment reports. And that's where we're interested in today. So when we think about users of the database and actions that may be parted on them, here is a threat analysis process, which you can find published in my PhD. And essentially, it has an operational systems view and then a model creation type of view with some recommendations along the way for countermeasures. If we break it down, we can sort of see that there's a filing and separating of conflicting data. There's a prioritization of the TVACD task, or the analysis tasks. There's a parameter assessment, functional analysis, and system vulnerabilities and strengths, followed by a grouping analysis and some viabilities on, say, JSR, intercept range, detect range. And then what that might do is help us to build and understand and prepare a software model for testing, and the engagement dynamics and the guidance laws, etc., that go with that help us to consider the agility required and the tempo or the time of flight that the countermeasure has to be effective. We can also consider that there's some TVACD tasks that are required, and we would consider what models we need and what TVACD tasks are required from the recommendations of a certain part of a kill chain may result in a certain kind of countermeasure, and there may be one or many of those kill chain parts that we assess. So that's the number of tasks and the number of software models required. And then we go into a modeling phase, and the first thing to do with that is create a model and test that we have entered it and built it correctly so that it responds in the way that we expect. And that's basically a modular parameter, model parameter construction and testing for data entry. The next part of that is lethality matching. Does this model reach the stated or expected lethality of a system? And then what we might do is also do some testing to see that it reacts to countermeasures correctly, i.e. it responds in the right way. And then there might be some model robustness also to help uncertainty in the data. Then we might move to the actual targets and actual equipment, and there we might do an actual lethality, which is a susceptibility assessment between the actual equipment and platform and the actual threat models, and see how susceptible they are as a lethality assessment. We'll build on from that with the generic countermeasures of that system, and that gives us a palette of techniques in which we can sequence and optimize. And then we might do a stochastic assessment for the final susceptibility assessment to provide a pH, pK, that kind of thing. And that kind of probability of escaping hit or probability of kill will help us to inform the operational decisions. In actual fact, it can be promoted to battlefield simulations. Okay, so that's one kind of action that occurs on the database. Another one might be to do with the intelligence cell and the Intel lifecycle. And what we can see here is the Intel lifecycle going between direction, collect, processing, analyze, disseminate, feedback. And along that way, we may have information stored. So we can see that the direction might cause questions, and the questions might cause raw data, and the raw data might be processed information, and the information might be analyzed into intelligence, etc., etc. And what we could probably quite reasonably assume is that parts from the previous stages might be related to these stages, and that's not uncommon to have that kind of thought or theory, that there is some kind of building of transformation which is also database related. What, however, is less obvious is in actual fact it also relates to the processes and procedures that actually went into those, and how we store or record or mark up what those processes that were actually performed were. And that is far less obvious, and that tends to be an area where traditional CEMA or electronic warfare databases are not as strong because they are data-centered only. We could also consider the operations section, and they also have some processes, and there are some ideas about how processes that might occur. But what we have to realize is in the sort of OODA loop type process of observe, orientate, decide, and act, that some of these actions may only be available if information or preparations were available, etc. So there is some alternatives in the process. And so what we can say from that is that the databases, particularly relational ones, tend to have some advantages of being very strictly syntaxed and having very strong semantics about the fields and what they are. They have pure data models which tend to be decoupled from human actions or even machine operations. And the data items described are very well described as a common understanding for every user. What that then brings up to us is some difficulties that occur with that, which is trying to capture the actual processes that were actually performed other than the data. Now, the reason why databases are so strong in this respect and are so used prolifically is reprogramming, where there tends to be a one-to-one relationship between programmed field and the data stored. Where they are weaker is in the intelligence of the field, where the data is matured, evolved, and changed, and where they tend to also be a little bit weaker for databases. In fact, even the database approach is when there are processes that need to be recorded and are not necessarily the same process each time. What you kind of need then is less of a database and more of a markup language. So So what we kind of want going forward is support the concept of generic threats, which is to make a prediction that something is threatening rather than respond to an engagement that occurred. We want to be able to proactively know that this is a bad thing and perhaps unleash a generic countermeasure which is adapted for that threat and that engagement at whichever kill chain stage. What we also want to be able to do is deal with irregular data, and what we want to be able to do is record in some way decisions other than data and processes that were performed other than data. It's kind of like a markup language. And so the goals really that we're overridingly looking at is automating parts of the TVACD process and optimal tactic selection. But there are other elements within an EW database which are equally applicable to this, particularly in operations and in the intelligence lifecycle, which we already highlighted. So the approach to this is to use a programming language and a markup language, which allows us to, when there is missing data, be able to calculate the values from other fields, and which might be in different quantities, which might be available for one system and not for another, etc. And so this idea of something called a computational graph also embraces the idea of database multiplicity. We can see a sort of computational graph here, which is that formula at the top, x equals a plus 4 plus b times c, and we can see that represented as nodes. And what we can find is when we put different regularities or different amounts of information into those variables, what we get is the relationships for databases of one-to-one, one-to-many, or many-to-one, and many-to-many. And this can be used to help us use a formula and expose that formula in a way between database records in order to calculate values when they're not available. So for an example, we could assume that we are missing some sort of antenna beam width, and we know that there is a body of knowledge of information that we can code, and that might be the theta k lambda over d type derivations, and we can see a number of examples there. We'll immediately notice that one of the k values is 1.33, is quite markedly different, and we would expect that there's some kind of outlier that comes because of that. And if we then use some metadata, that helps us to abstract from the different formats of the different inputs and convert to a similar format to make things a little bit more able to be reused. And we can see from here that those database records can also be converted into axioms, and we could be able to calculate some of the values in order to go and use this approach for a markup language using computational graphs. And what we can do is also add some fact elements here. We can see that we have some formulas for calculating the carrier frequency when we don't know it from other values. We can even calculate wavelength lambda from some values, and we're going to assume that we don't know what the antenna type is. So what we might find is what we want is to code this up in a way that we should be able to make some kind of judgment or assessment based on the entire body of knowledge that's available to us. And what we could do therefore is we could calculate those values, and we can see the values have been transformed, and we have a number of values, and indeed there is an outlier value with the Yagi array. And what we can then do is histogram that data and take a center of gravity to give us the one value we are going to use for reprogramming. So in this way, what we have done is taken variable amounts of inputs from variable assumptions from the body of knowledge and converted to a single most representative value. And we also get a confidence for that value and a certainty. We can play some games with this, and if we remove the outlier, we can see that the confidence increases because things are becoming quite confirming of each other. We could add a additional fact, and it might raise the confidence again because it might be confirming one of the values, in this case the uniform para dish, and we can see that that therefore is having beneficial effects for dealing with outliers and also dealing with confirming information. That is fairly simplistic, but if we were to add more uncertainty into this, say some more values for the antenna diameters, what we find is the histogram becomes a bit more complicated, and therefore the number of permutations. But we're still able to resolve the most confident figure for given the entire body of knowledge and its uncertainty. So what actually is happening here is that we have an amount of inputs which are going into an input layer, and there's a metadata layer converting this to a common format. There's a number of hidden layers going on with axiom rules, and then there is an output and a histogramming approach which provides that single value. And what we can imagine, therefore, is these input, hidden, and output layers are very like neural networks. And the input value that we have taken, where they are got irregular inputs, where there is more than one example, virtualizes those. So it now starts to look like a neural network expert system hybrid. And it's still doing the same thing, which is taking multiple inputs and producing a singular best value with a confidence. So in summary, what we've done is calculate a prediction based on the body of knowledge and facts. And that has enabled us to take that area of an amount of data and produce it into a single solution for reprogramming. And that should be able to help us with generic countermeasures for calculating missing parameters given an engagement or given weighted values that is to occur in the future. The irregular data can be from 1 to 1, helps us to map that difference from the raw data, information, intelligence transforms using the atoms and axioms. It supports the best value for a fixed database model and supports variable instances while also providing a confidence with it. It aids the infilling of data, and it also would aid the transport of data or the data migration from one database to another. It considers the outliers and provides a confidence. It provides evidence of how the value was arrived at and tracks the security level, and it allows machine operations to be encoded because it's a markup language. These are small amounts of analysis that can be carried out, and they can be carried out completely in every case, or given selections on guard equations can be reduced in some cases, so that it always represents the valid body of knowledge. So what we can say is the data that is provided represents the known physics, and the value that you've given, the value that you were given represents the totality of the body of knowledge as best value fused together. If the amount of knowledge changed, like the antenna type changed, then the amount of the body of knowledge that would be valid would be different, and therefore the value would change to be a subset. And so what we're always getting is a confidence based on uncertainty, and we are always getting a value which is based on the complete body of knowledge. It has obviously the applications to threat analysis approaches and vulnerability reports, and it supports optimal tactic selection with weightings using those Bayesian confidences. In conclusion, it's a layered approach that abstracts information for reuse. It has irregular inputs from the computational graphs, which provides that input population diversity mapped to a histogram for reprogramming purposes. And the computational graph provides alternative values to fill into raw data. The guard equations manage the body of knowledge to what is valid for the scope, and the EW database has been abstracted with virtualized neurons which map earlier to the intelligence data as we saw before, but it also has effectively a markup language to say what things were combined from what inputs, and we can therefore capture what analysis was performed and what analysis was not, and that could normally be regulated by those guard equations. There's a number of publications that have been produced on this subject, and these are those. Thank you.